So hi again, it's Mike Sholin here from CLASP, and I was just waiting a few more minutes for folks to join us. So we're spanning a lot of time zones today. I know there's some folks joining us from California quite early in the morning for everybody there, the afternoon and elsewhere on the planet. Yeah, so thanks everyone for joining us. I think I'll just go ahead and get started. We're 3 past the hour. We have about 40 participants on the line now, so I think that's good, and maybe a few more will join us as we go along. So as you all know, this is the second of 2 training sessions that GTD is putting on for everyone. The last one was held 2 weeks ago, and if you happen to miss it, at the end of the GTD slides today, Thomas and Yuan will give you a QR code and a URL link to the team website where you can download the slides from last week, download and or watch the video, the recording, and catch up on other material there, the software tool itself, some of the papers and work that's been done around this. It's all posted on that page. So we encourage you to go there and have a look. And today's recording, today's session is going to be recorded. We will also be posting these slides and the recording on the same page. So that'll happen, within a day of the session. So you'll be able to access that tomorrow and share the links with any colleagues who were not able to join today. So today is training session 2. We were referring to this as the sort of more advanced training session. It's going to be looking at changes to the worklet characteristics and configurations, developing profiles for different computer test configurations that you want to conduct, and also having a detailed discussion or more detailed discussion on the results method, analyzing the output from the software tool, the aggregation of those results, and so on. So those are the pieces in line for you today. Unfortunately, Andoni's not able to be with us, but Thomas will be speaking first, and then Johan second on the results piece. And as before, I would encourage you all to post questions to us in the Q&A session. What we'll do, we've got 3 sections and for today's talk, and Thomas has a agenda there that he'll share when he starts. At the end of those sessions, we'll have brief clarification questions. So if you have any questions around clarification, please ask those at those points. And then at the end, after the talks, then we will have a more general discussion about the day and any other remaining questions that you might have. So please do use the Q&A session, and we'll be posting those Q&As on the team website as well. So folks who missed that will be able to catch it. Okay, I'm going to stop sharing now, Thomas, so you can grab control.
Thank you, Mike.
Yep.
Let me share my screen.
I can see that. It's
perfect.
Yep.
Thanks. So welcome again from GTD. This is Thomas speaking, and I will be going through the first 2 sections of this webinar. Today we have 3 sections, as Mike already outlined. First, I will be talking about the worklet modification, and then about selecting worklets and creating collections of worklets, and then Johan will talk about the results analysis. Okay. For the worklet modification. For that to be possible, we first need to understand a few things, which I will go into detail before I tell you how to actually modify a worklet. So we need to take a look at the file structure on the USB key and on the unit under test, so that you actually know where the files are you want to modify. Then we need to use the command line interface of the test software, because with the graphical user interface, you cannot do any of these advanced tasks. I need to show you how a worklet is internally structured so that you understand how it's built and how you can modify it. And then we will also take, of course, a look how the worklets are then configured or parameterized and grouped into test suites. First of all, if you plug in your USB stick you created with the software image you can download from our website, you will see the following folders on that USB stick. So there is a folder with the software for the controller PC, which does the acquisition of the data from the power meter. Then we have 3 folders for dependencies for the 3 supported operating systems. Those are mainly installers for example, the web browsers we use in our worklets and other stuff. Then we have a download cache, which basically contains all the data which is necessary to install the worklets. We have the source code for PHORONIX test suite, which is the actual test framework. We have a folder called PTS config. PTS is for PHORONIX test suite, of course. This contains all the configuration for our worklets. We have a scripts folder, which controls our test runs and automates everything you can also do from the graphical user interface, but I will go into more detail in a minute. We have 3 folders for the software to actually communicate with the power meters, and we have a folder for test results. There are also, of course, the executable files for the unit under test and the controller graphical user interface, which you have already seen in the last webinar. Once you install the software on the unit under test, you will get an energy efficiency testing folder on the desktop. And within that folder, you can find, again, the PHORONIX test suite, because you will not have the USB stick plugged in all the time on the unit under test. You will move it to the controller computer. So you obviously need the PHORONIX test suite here. And you also need the scripts folder to be able to conduct any tests and control the test runs. And of course, you also need the executable for the graphical user interface. Additionally, you need all the worklets and the configuration for those worklets, which is a separate folder in the user's home directory, which is called .PHORONIX test suite. As some of you might know, the dot in the beginning indicates a hidden folder on Unix systems, so on Linux and Mac OS X. But this folder is also hidden on Windows. So if you want to edit files in that folder, you have to change your Explorer configuration to actually show you hidden files. Otherwise, you won't see it. On Windows, this folder is located in C users username, and on Linux and Mac OS, this is the home directory of the logged-in user. The PHORONIX test suite configuration itself contains, again, 2 folders. One is for test profiles, or what we call worklets, and one is for test suites, which are these groups of worklets which we want to create today. Basically, the test suite is what you would call a collection of worklets which you can then, for example, use to test a computer of a certain category, like, for example, an office PC or a gaming PC. Yeah, but we will take a look at that later on. Here's another visualization of that folder structure on the USB key. Maybe it's a bit more visual if you see multiple folders at once. So we have the controller PC here with a few files, the dependency folders. I left out the other 2 for Mac OS X and Linux because it doesn't fit on the slide anymore. Here you can see the dependencies of PHORONIX test suite itself, which are necessary to run it on Windows. In the download cache, we have, as I said, the installers for all the software which is needed. For example, we have Blender in version 2.81 for each of the operating systems. And we also have test data. For example, this here is a video for the video encoding test, which is also located here. We have the exe files for the graphical user interface. We have the PHORONIX test suite. We have the driver for the power meters, the scripts for updating the USB key. And then we have the important folder, the PHORONIX test suite configuration with the test profiles and the test suites. Usually those profiles and test suites are grouped in a namespace. We just called it local because it's local to your computer, not coming from the internet. And then you have, for example, the Blender worklet defined here with a couple of files. I will go into more detail what's in these files in a second. And similarly, you have the test suites also inside a namespace with the name of the test suite and then a file to define the test suite itself, which is then listing all the worklets with all the parameters you need. We also have a user config.xml file, which is used to configure PHORONIX test suite. Like, for example, it contains the path to your download cache and where you want to install stuff and so on. Usually you don't have to change anything here, just that so you are aware there is another configuration file here. And finally, we have our script files, which can be used to run a test or to install everything or to uninstall everything, of course. Okay, so now that we know how the software is laid out, at least roughly, we can take a look at what is necessary to be done for changing the software. There are basically two methods. You can either change the software on the USB key, or you can change it after installation on the unit under test. Both methods have their advantages and disadvantages, and I will go into those right now. So if you change the software on the USB key, obviously you have to change the desired files to make your change. Then you have to reinstall the software on the unit under test to actually get your changed files on the unit under test. This will of course not reinstall everything from scratch, but only transfer those files which are actually needed. So it should be relatively fast. And then you can run a test through the graphical user interface or the command line interface, just as usual. There is one thing to keep in mind here. If you run the update script to update to a new version, this will revert all your changes. So if you do this method, then you have to make sure that you copy away your changed files before you do an update. Otherwise, it's gone. Of course, this test method is mostly useful if you already know what to change, or if you already have changes which you have confirmed are working and you want to try that on more than one unit under test, because then you can just use the same USB stick to install it on all computers you want to test. So for a start, I would recommend the other method, which is changing the software on the unit under test after installation. So you do the installation as usual according to the test procedure. And once this is installed, you change the desired files either in the folder on the desktop or in the folder for the PHORONIX test suite configuration in the home directory. With this method, you can then just continue your test run as usual without having to reinstall something or copy anything over again. Of course, there's also a warning to that method. If you then reinstall the software from the USB key, it will also overwrite all your changes. Yeah, as you might guess, this method is useful if you want to quickly try something, or if you are not yet that familiar with the structure of the software and you do your first changes. I would recommend this method because it's just a bit faster, because you don't have to reinstall the software and go through that extra step. Of course, you don't need to be worried about breaking anything, because either you can fix your mistakes by reinstalling the software or by running the update script if you do the other method. So you're always on the safe side, and I don't think there's a big risk of breaking something. So now we have to take a look at the scripts which are available within our test software distribution, because you will use those scripts later on to actually do changes, run worklets, create test suites, and so on. You might remember this slide from the last webinar I presented 2 weeks ago. So you basically have scripts for every task which you can do with the graphical user interface, but there is one script which is printed in bold here, which allows you to run basically any command PHORONIX test suite understands, which is quite powerful. This script isn't used from the graphical user interface, and until now we only used it internally, but now we want to give you the chance to actually do some advanced stuff, and I will show you what you can do with this script. But first, let me tell you how to execute the scripts in general, because it's important that you run them from the correct directory. So if you run a script from the USB stick, for example, to install the software on the unit under test, you would do that directly from the root of the USB stick, not from the scripts folder. That's important because that won't work. So for example, on Windows, you would change the directory to the root directory of your USB stick. In this example, I have on the slide, it's drive E, and then you would call scripts / Windows install uut.bat, for example. Or similar, if you already have it installed on the unit under test and you want to now run a test run, or maybe start the result viewer or whatever, you can do that. For example, here on Mac OS X, you change your directory to desktop / energy efficiency testing, and then you call the script with ./scripts/ whatever the name of the script is. So to use this PTS script, as the name is, you have to know about the commands understood by PHORONIX test suite. Those are all listed in the PHORONIX test suite documentation. I have the URL right here on the slide if you want to dive into it even more. But the most important commands are usually the ones I have listed here on the slide. So you can, for example, list all the installed tests. You can list all the installed test suites. You can get info about a test. So this is what version the test has, what name it has, what dependencies it needs, and so on. You can install a test. So that means installing all the dependencies, extracting the test data. You can run a test with the run command. You can do a debug run, which is very useful if you have a worklet which doesn't behave like it should. And you have a build suite command, which is actually very convenient to create collections of worklets for your customized testing. In each of the commands, you have to replace test name with the name of the worklet. And the name of the worklet, you can find those names with the list all tests command or with the list install test command. And it looks, for example, like local /AO bench -1.0.1. So you have the namespace where the worklet is located, the name of the worklet, and the version number. If you want to take a look what worklets are available, so there is a website called openbenchmarking.org, which lists all the worklets which are known to the developers of PHORONIX test suite, and you can just go into those and check out what is available instead of creating your own worklet from scratch directly. If you go to that website, you can click on tests in the navigation bar in the top, and you will get a list of all the available worklets. It's quite convenient. You can directly see which operating systems are supported. So you can see, for example, the AI benchmark alpha worklet, which I have on the slide here, is supported on Linux. That's the little penguin and the Apple logo. So it's supported on Apple. And I think the last one is FreeBSD, which is not really relevant for our activity. So you can already filter the worklets here. So for example, Windows is not supported for that AI benchmark worklet, so it will most likely not work on Windows. So let's say you have found a worklet on this website, which you want to try. And I have actually found one, which is quite interesting for the purpose of this presentation today, which is a worklet which does video encoding with the AV1 codec. And one could have the idea to compare this to the X264 worklet, which we have included in our test distribution. So we will go through the process of setting up this worklet and trying to run it in the next couple of slides. So first of all, we have to install the worklet. So we open up command prompt on Windows in this case, but yeah, it's similar on Mac OS X. You would use the terminal app, and on Linux, you would use whatever terminal emulator your distribution comes with. You navigate to the folder on the desktop, and then you would run the PTS script with the install command and the name of the worklet, PTS AOM AV1 version 2.12. You can then see that PHORONIX test suite is doing its job, like evaluating the dependencies, determining what it has to download to fulfill those dependencies of this worklet. So for example, it needs the Perl programming language, which it will download to the downloads folder and then install it for you. Please note that we have spent quite a bit of time to make the installation of our worklets as automated as possible. So in that case, there will be the installer of Perl popping up, and you have to click next, 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 next to actually finish the installation. After that, the PHORONIX test suite will determine what else is necessary to run that worklet. So it needs the test data, of course, and the implementation of this video codec to actually do something useful. So it has determined it needs 2 files to download, which is 5.8 megabytes, and one file which is already in cache, which is 640 megabytes. This is the test video, and it will tell you how much space is required, 950 megabytes of space for the installation. Then it will grab the file which is already in the cache, download the remaining files from the internet, and install it. And once you are back to the command prompt, without any errors, hopefully, you can go ahead and try to run the worklet actually. If we do that, again, with the PTS script, the command is run and the name of the worklet. We have to first parameterize our worklet because we have not told PHORONIX test suite how we want to run this worklet. And we can see that we are given a menu with 6 options where we can select which modes the encoder should use. And in this case, I just decided to use the first one, and I typed in 1 and pressed enter, and then the process continues. It will tell you that system sensors are locked. This is defined or done by the PTS script, this setup, so you don't have to do that manually. And then it will start to actually run the test. In this case, you can see that the worklet doesn't work as expected, so you only get the test run did not produce a result, which is quite unfortunate. So you have to actually take a closer look at that worklet to find out what's wrong. We can do that with the debug run command. So we launch the PTS script again, this time with the debug run command and the name of the worklet. Again, we have to do the parameterization. We use the same parameter as last time, typing in 1 again. Then the worklet starts again, but this time we will actually get quite a bit more useful information. for debugging what's happening. First of all, we get the command which is run by PHORONIX test suite. So basically what PHORONIX test suite does to start up that worklet is change directory to C users, tests, PHORONIX test suite, install tests, PTS, AOM, AV1, etc. And then it will run a script or an executable, AOM, AV1, with a few parameters. And then we also see the output of this command, which is unterminated S command for a set expression. Okay, that's maybe for most of you a very technical term, but if you're familiar with the tools behind that, you can already kind of guess what's happening. So my next step in that case would be to take a look at this AOM AV1 file to see what's actually happening. If we open that file in Notepad, we can see the set command in the second to last line. And we can see that there is, for whatever reason, a $sign in here, which doesn't belong there. I don't know, maybe it's a typo of the creator of the worklet or wherever that comes from. So I went ahead and removed that $sign. And we can run the worklet again in debug mode. And this time we actually get a valid result with 14 frames per second on this particular machine. So that would be one of the procedures to look into a worklet to see what is happening and to fix a simple error in the worklet. Obviously, our worklets should hopefully not have such errors because we have actually tested our worklets. And obviously, this worklet from openbenchmarking.org was not tested very thoroughly, it seems. Of course, there are a lot of other reasons why your worklet might not work at all or not behave in the way you expected. So for example, the software you use might not be supported by the operating system, or maybe there is no corresponding install script for the worklet, so it just doesn't know how to set up everything on the corresponding operating system. Maybe your source code doesn't compile because your compiler on the operating system is too old or too new or whatever. Maybe you have missing dependencies, like for example, a system library or any other application which is needed to run the worklet. Or those dependencies are maybe not set up correctly. So it's sometimes quite complicated to actually find out what is happening when a worklet doesn't behave as it should. But with those commands I showed, you can hopefully get an idea. Also, if you encounter any problems with our worklet, of course, it would be nice if you can run at least the debug run command. That gives us a lot of information, which might help us in debugging. And yeah, also, if you encounter any problems in the future, you can drop us an email and we might look into that. Of course, we cannot support every worklet on openbenchmarking.org. That's clear. But yeah, if there are any questions in the future, drop us an email. So to further understand how the worklets work, we will now take a look at the files which actually define or declare a worklet. So there is a TEST-DEFINITION.XML file. This, for example, defines the test's names, the external dependencies which are needed, any options which the test might offer. Then we have a downloads.xml file. Here are all files listed which need to be downloaded from the internet or which need to be in the download cache for the worklet to be installable. And then we have an install script with the name install.sh, which then actually sets up the worklet and installs dependencies and extracts test data, whatever is necessary to get it working. And this will also create the script which is then used to run the worklet. Usually this file is executed on all operating systems except when there is an install Windows or install Mac OS X file. because oftentimes, yeah, you need different setup instructions to be executed on Windows or Mac OS X. So there is this possibility to have these separate scripts. Lastly, there is the results definition file. This specifies how to get the performance result. So usually the software which you use to do the test will only output text to its standard output channel. And you have to specify how to actually retrieve the information from the worklet, basically. So now we can take a look at each of those files. I think I will just tell you the most important things about the file, as we don't have time to go through all or through each and every line of these files because it's just too long. Also the file, sorry. Also the files are a bit shortened because otherwise it would just not fit to the screen at all. Okay, so in the test definition file, we have the title of the worklet, which is Blender here. So I took our Blender worklet as an example. We have the version, we have the result scale, so the performance result, which is in seconds in this case. We have the result proportion. In this case, LIB means lower is better. The other one would be HIB, higher is better. And we can specify how often the worklet should be run by default. So it will do, in this case, at least 3 runs. But of course, there is then the automatic repeating of worklets according to stability of the results, as I have shown in the last webinar. We can define a version of the test profile or of the worklet, so to speak. We can declare which platforms are supported and what the dependencies are. And then we can actually define our options for our worklet. So in case of the Blender worklet, we want to render 3D models in this case. And there are different available 3D models, and there are different available rendering modes. And you can combine those two options in all ways or in any way. So for example, here we have the BMW model, and we have the classroom model, which are defined as a menu entry. And then we have a second option, which is the compute mode. So this menu of the compute mode also has 2 entries, which is CPU only and OpenCL. And for all of these entries, the given value, so this is in case of the 3D model, it's the path to the model file. And in case of the compute mode, it's just a text to specify which mode. This will be appended to the command line arguments of the script, which then actually runs the worklet. The next file we want to look at is downloads.xml. Here we can see that there are 4 files specified for this worklet. So we have the actual Blender program for Linux, for Windows, and for Mac OS X. And then we have a zip file with the 3D models which are used for the test. For each of those files, there is an MD5 sum and a SHA-256 sum. Those are used to verify that the download was actually successful and that you got the file you expected and that everything is correct and not someone is exchanging the file without you noticing. Next up, we have the install script. In this case, this is the install script for Linux. And what it will basically do is unzip the Blender application and unzip the test data, then move the test data to the expected location, remove everything else from the test data which we don't need, and then it will generate the run script. Now this looks quite complicated and it's actually sometimes quite hard to debug if there is something wrong here. So it's usually better to look at the generated install script after the installation is complete than to try to understand all the escaped dollar signs and quotes and whatever here. If you're familiar with shell scripting on Linux, that should hopefully be not too big of a problem, but I think it's quite challenging for most of us. Then we have the results definition file. As I said, this is used to define how to extract the performance result from the worklet. So your worklet might, for example, measure how many frames per second are rendered or something like that. And this will be outputted by the software to its standard output channel. So for example, if you have a game which is rendering a scene, it might then print this result, and we have to define here how to get actually the result without anything else. So here we say a line hint, so we only want to have lines which contain the word saving, and then we define an output template on that line. So we say there is a string first, time, colon, and then there is the result with this special marker, and then there is some other text. So basically what we will extract from this line is everything between time, colon, and the saving thing in parentheses. Okay, that would be so far the first chapter regarding the setup of worklets and this internal structure. Do we have any questions?
Yeah, Thomas, are you able to see the questions in the Q&A? If you hit that button, we've got a couple questions from John. Soondragon waits. I can read them to you if not.
Okay, yeah, I can see them.
Okay, maybe if you
So
read them first, yeah, and then
yes.
thank you.
Okay, so the first question would be from John Sundragon Whites. Please describe the update script function a little more. Does it pull the latest software from the internet? Does it update the USB key image directly? Okay, for the update script, yes, it will pull the latest software from the internet. Yeah, it's quite intelligent, so it will only transfer files which have changed from the release you have to the newest release. So usually when you already have a USB stick, you are encouraged to use the update script, because that will just be much faster than re-downloading the huge image file and creating a new USB stick. So basically, the update script goes through all the files on your USB stick and compares them to the newest version on our server and eliminates all changes. Okay, then we have another question from the same person. My recollection is that effort has been made to normalize performance measurements for the selected worklets so they can be compared. Importing another PTS worklet may lead to output units that were not covered by the normalization, correct? I would say you can import worklets from openbenchmarking.org. Of course, this does change your efficiency results. If you change the set of worklets, this will always be the case. But nevertheless, the result unit itself doesn't matter too much. I think we will see this in the last part of the presentation when Joan explains the formulas, how the results are actually calculated. So yeah, there is more information ahead, but to say it like this, the result unit doesn't matter too much, and the normalization will still work. Please note that there is no weighting of the worklets yet. This is still a topic to be discussed. So, of course, if you pull in a new worklet, this would also have to be weighted relative to other worklets. But this is still a ongoing process for all of the worklets. So that's not a problem right now. And then we have the last question, supplemental to previous question. For example, the example codec test output results in frames per second. Maybe the current scripting knows how to deal with that, maybe not. Yeah, as I said, yeah, frames per second is already a unit we have for several worklets, but even if it would be a new unit, it wouldn't be a problem at all. Okay. Then I will go on with the second chapter of this webinar, which is the worklet selection. So for now, we have seen how to run a single worklet, but of course, this is only so good. So if you have 40 or even more worklets, you don't want to run each worklet by hand on its own, taking power measurements for each of the worklets manually. That doesn't make sense. So we need to have a way to group those worklets into categories and actually tell PHORONIX test suite how these worklets should be parameterized so that we don't have to type in parameters every time we run the worklet, and so that we have a specific order, a specific set of worklets, which can then be run in an automated, repeatable way. So basically, this is done through another XML file. This time, as I said before, in the directory structure, it's placed in the test suites folder inside of the PHORONIX test suite configuration. So again, this would be in the PTS config folder on your USB stick, or on in the .PHORONIX test suite folder in the home directory of your user once you have it installed on the UUT. To create a new test suite, there is a command of PHORONIX test suite which you can use. The command is called build suite, and it will ask you for a few generic information, like the name of the test suite, the test type, basically which subsystem of your computer will be tested, but yeah, you can choose whatever you want, it doesn't really matter. You can give the name of the maintainer of the test suite, so you can type in your name or anything basically. You can give a description so that you know again what the purpose of this thing is. And you can specify whether you want to pin the versions of the test profiles, or if you just want to pull in the newest version of the test profile every time you run it. So I have an example here how to create a test suite. This time it's on Mac OS X instead of Windows, but yeah, the process on Windows and on Linux is essentially the same. So we are here on the unit under test. We have installed the software. So we are on the desktop in the energy efficiency testing folder. And we can call our scripts with /scripts/Mac OS X PTS, and then give it the command build suite. PHORONIX test suite starts up. It asks us to enter the name of the suite. So I just chose my worklets. It gives us a few choices of the test type. As I said, you can put in anything. It's basically just a tag to sort your test suites if you have a lot of them. You can enter the maintainer name. I put in my name. You can put whatever you want. You can put in a description, like I just put my favorite worklets. You can put worklets for office computers if you're doing something like that. And then you can say whether you want to bind to the versions of the test profile. This depends a bit on what you want to do. So if you want to have a fully reproducible set of worklets, you would want to pin the version because you don't want the test profile changing potentially the outcome of the test. But if you're just experimenting, you can also pull in the latest version. It doesn't matter in that case. If we type in yes in this case, the script continues and it gives you three options to either add a test, add a sub-test suite, or save and exit. In that case, we want to add a new test. So we type in 1 and press enter. Then it gives us a list of all the known worklets, which is around 500 or 600. which are currently available. So the list is quite long. Yeah, I will just take our Blender worklet, which has the number 2 here. So I will remember this 2, and then just type in 2. You can see the list I got 508 worklets when I created this screenshot. So it's quite a lot. Yeah, we enter 2, and it will tell us this is worklet Blender version 1.6.0. And then it will ask us for the configuration options so that we don't have to specify those configuration options again when we run the test suite later on. We can now say which 3D model we want to render. So for example, the BMW one, then we type in 1, press enter. Then we get the second choice, which compute method we want to use, CPU only and or OpenCL. There are a few more. Like CUDA or NVIDIA Optics. I think they are not supported on this system under test, so it will not show up. But in this case, I decided to do all options. So I typed in 3, so I will get CPU only and OpenCL. Then we are back in the previous menu, so we can decide whether we want to add another test suite, or just save and exit. In that case, I chose save and exit. If you want to add more tests, yeah, you type in 1 again. Otherwise, for save and exit, you type 3 and press enter. PHORONIX test suite will tell you that the test suite was saved, and it will tell you the command to run it. Of course, it doesn't know about our script, so it just tells you to run PHORONIX test suite with the benchmark command, which is the same as run. And then the name of your newly created test suite, which remember on the last slide, we defined it to be my worklets. So again, it's my worklets to then run this test suite. If we take a look at what happens behind the scenes, we can see that there was a XML file created, which looks like this. So we have all the information we typed in, like the title, the version, the test type, description, and maintainer. And then we have the list of worklets which are defined to run within this test suite. So here we have 2 tests because we selected 2 compute modes and 1 3D model. This means 1 times 2 equals 2 tests. If we would have selected 2 3D models, it would be 4 tests because you would get a test run for every compute mode with every model, so all the combinations. We can see that the test key actually specifies the test profile, or the worklet as we call it. The arguments specify the command line arguments to the test script. So in this case, this -b gives the input file, which is the 3D model in this case for Blender. We give it an output file where we want to save the result of the test, and we give it the format. It should be a JPEG image, and then we give it the compute mode. Of course, this is different for every worklet, so depending on what kind of software is used to create this worklet, those options look completely different. Finally, we have the description. This will then later on show up in the test results so that you can actually identify your results. So you see again which 3D model was used and which compute mode. Of course, we want to tell you which parameters we use for our worklets so that you can actually create new test suites with our worklets and our parameters. So for Blender, we have the BMW model with CPU only and OpenCL, as I just showed. For Appleseed, we use 3 different rendering scenarios, which are Emily, Disney Material, and Material Tester. For the set standard compression, we have set the compression level to 19. For Selenium, we have chosen Firefox and Chrome. For IO-Zone, we use 4 kilobyte records with a 2 gigabyte file size, and we do read and write tests. For T-Test, we have a test run with 1 thread and 1 test run with 2 threads. For cache bench, we use all available options, read, write, and read, modify, write. For SQLite, we have one run with 1 thread and one run with 8 threads. For OS bench, we have selected the create files, processes, threads, and memory allocation tests. For the Da Capo bench, we use the H2, JSON, and the trade beans test. For ParaView, we have wavelet contour and wavelet volume. For OpenArena, there is the option to set the screen resolution, which we have set to Full HD. For Xonotic, again, Full HD resolution and the ultimate quality preset. And for the Unigine benchmarks, we have Full HD again and OpenGL rendering. So with this information, you should be able to use our worklets within your test suites. So when you are prompted for the parameters, you can type in the parameters from these 2 slides. All worklets which are not listed on those 2 slides have no parameters. So you should not be asked for any parameter if you use these worklets. Before you conduct a test run, you have to know about one last thing to parameterize your test run. This is done through environment variables. And there are basically 2 environment variables which are interesting. You can define a variable called skip tests. If you have a test suite, for example, which contains a test which runs very long and you don't want to run it right now, but all the other ones, you can use that skip tests variable to skip one or more tests. You can use the force times to run variable to specify how often a worklet will run. So by default, it will just use what is specified in the test profile plus the dynamic repetitions for stability. But if you want to say, I want just one run of every worklet to see if it actually produces results at all, then you can use this force times to run variable. To set such a variable, you can use the set command on Windows or the export command on Mac OS X and Linux. I will show an example on the next slide. We have a software update coming up. I will give a few more details towards the end of the presentation. And it is planned to have a few new environment variables for feature requests we have received in the past. So there will most likely be an environment variable to set a time or a delay, I should better say, between worklets and worklet repetitions. This will then allow you to test whether the thermal condition of your system makes a difference for the performance result. Again, this will be the next software version, which is not released yet, but more information on that towards the end of the presentation. So now to conduct a test run, we can again change directory to our energy efficiency testing folder on the unit under test. Then we can set our environment variables if we want to. We don't have to, then it will just use default settings. And then we can run the PTS script with the run command and the name of the newly created test suite. I have an example for Windows and for Linux. For Mac OS X, it's basically the same as on Linux, except that you would write Mac OS X PTS instead of Linux. On Windows, you have to do the slashes in the other direction and use the set command instead of export for the environment variables. But apart from that, it's relatively similar. Okay, that would be chapter 2. Maybe we have some more questions.
Yeah, there was a question Steve Eastman asked in the chat, just if you're going to share the criteria that were used to choose the 46 worklets in the software.
Okay, I think we have given a bit of an insight last time, so 2 weeks ago in the webinar. Basically, our main criteria are the worklet has to work on all supported operating systems. It has to work reliably, so it shouldn't fail randomly or whatever. It has to produce stable results so that you can actually reproduce results if you run it the next day or 2 weeks after. And it has to make a difference between computers where you expect different efficiency. It should actually result in different efficiencies being reported.
Okay, let's hope that addresses your question, Steve. And there's a couple Q&A box ones. Can you read those, Thomas?
Okay, so we have one from Anson Wu. Can the test be configured to select the highest performing option automatically? For example, selecting between CUDA OpenCL and CPU for the Blender worklet. No, this is not possible. And I would also say it doesn't make a lot of sense if you have a computer with a high-powered graphics card. You wouldn't want to compare the CUDA performance of that one to a CPU-only rendering on a different computer. Yeah, I don't know if this is something which could make sense, but this is not something directly supported, at least, to directly answer the question. So in that case, if you wanted to have that, you would do a test run with all 4 of the compute methods, or all 3 or whatever, and then compare the results by hand in that case. Then we have another question from Steven Fernandez. Is there a list of all 500 worklets with information about the components each stresses? There is a list, yes. You can go to openbenchmarking.org, which I had also a screenshot in the presentation, and you can find all the worklets there. There is some information, at least, about each of the worklets. Usually they have a short sentence describing what the purpose is or what the background of the worklet is. To actually see which components it stresses, I think you need to take a deeper look and actually check out the software which is behind the worklet. So for example, Blender or whatever the software is which is actually used. Usually you don't get as much information as you might need from the PHORONIX test suite side or from the open benchmarking side. Okay, I think that's it for the questions. Then I would give to Johan for the last part of the webinar.
Thanks, Thomas. So this is Johan speaking. Let me share my screen. So there you are. So I will present you the result analysis we do. How do we show you the result generated by the tool? Those who attended the previous webinar would remember that we already presented it, but today we will go more into detail. So where can you get the result? You can see them in our web interface that we already presented, but I will, just as a reminder, I will show it to you again today. And you can also export the result in CSV file, just in case if you want to treat them in more detail. We will see it later. The results we provide are just, or mainly, the performance of each worklet, its efficiency, which for the moment we compute as performance per watt, and the power demand during the whole worklet execution. So these are the results per worklet. Apart from that, we also provide aggregated results. We want to have a final value, which is a summary of all the execution of all the worklets. So then this is the aggregated result you can see here. So these results are a geometric mean of all the performances of each worklet, and also what we call meta performance per watt, which is just a global measure of the efficiency. It's just a single value that you will get at the end of the execution, telling you how efficient your computer is. This value by itself doesn't make much sense. It's not that useful. This value is useful when you use it to compare the result between different computers or different executions on the same computer. And of course, we provide the aggregated result, but you can also compute them by yourself with the values you can find in the exported CSV file. I will show that to you later. So I've told you that one of the aggregated results is the aggregated performance. How do we do it? This aggregated performance is the geometric mean of, and here we have to consider two cases. As Thomas mentioned before, there are worklets in which the performance is measured in terms of higher is better. So a higher result means a better performance. And there are some worklets in which is the inverse. A lower value means a better performance. So to compute this geometric mean, we take the actual performance of the worklet whose result is higher is better, and we take a conversion to higher is better for the worklet in which the result is lower is better. And how do we do this conversion? You can see it here. It's this simple equation. It's just we invert the performance, and just we add a scale factor so that the number is not that small. All the worklets, as we apply the same scale factor to all the worklets, this makes the result still comparable between executions on different computers. So no need to worry about this particular factor. Okay, this was the performance. What about the efficiency? The efficiency that we provide at the moment is the division of the performance on one side by the average power demand in watt. So as there are higher is better and lower is better worklets, we have to treat them, let's say, slightly differently, although at the end you will see that it's the same. So higher is better worklet, efficiency is performance divided by average power. Performance for higher is better worklet can be measured, for example, in frames divided per second, which means that the time is in the denominator, frames per second. So if we have a worklet in which a lower value is better, so a faster worklet, for example, it means less time, less execution time, the worklet is better. So what do we want to do? We want to do the same with the worklet in the denominator, 1 divided by the worklet execution time. So now this is what we consider our performance, and we divide it by the average power demand. We also have a scale factor here in this 10,000. Later on, I will show you why with actual number. Okay, so now we have computed the efficiency of each of the worklets. What do we do with, or what do we do if we want to get a final single value? As we did for the performance, we compute a geometric mean of the efficiency of each worklet. Why a geometric mean? Why not arithmetic mean harmonic mean, whatever. Well, as you can see here, so the most appropriate calculations, or the most appropriate mean calculations, if we want to combine values that do not have a defined weighting, as Thomas told you before, because for the moment there is no weighting between the worklet, is a geometric mean. So that is what we apply here. The aim of this training today is not to tell you why did we choose this particular metric, or what is the theory behind it, or whatever. The aim of the presentation today is to show you where and how you can get the result. But in any case, if the efficiency metric was another one, you could also always get it from the same place and in the same format. So what we will see right away, just in a couple of minutes, would be still valid. But in any case, if you are interested in knowing which is the background of this metric, you can just take a look at the paper that the white paper that we provide you in the website that you will just see at the end of this presentation. There we explain why we chose this metric, theoretical background, where is it also used, some examples, etc. But I repeat, today we don't have time to enter into details of why it is chosen. So I think the best is that we go now to a practical example. So what I will do now is just open the result viewer and just get through the result. If you remember from the last training, we can open the result viewer with this button in the controller computer user interface. So let me do it. In this particular computer, I have just a couple of results. This is the summary. These are all the results you have in your own USB key. So the more that you run, the more results you will have here. And these are per, let's say, test campaign. I have a couple of examples here. I will go through the shortest one because it's enough to present you what I want you to see. So I will not extend into the details here in the result viewer or in the web result viewer, because we already explained it in the last session. But just as a reminder, I will quickly go through it. So here at the beginning, we have just a summary of the characteristics of the computer you have just tested. Then we have a table summary of the performance of each worklet and the geometric mean. I explained you in my slide, this number here is not the geometric mean of the numbers you can see in this list, because you have to remember that worklets whose value is lower is better, the ones that have the small down arrow, have to be transformed to higher is better. I will do a quick exercise in a couple of minutes. And then what do we have? We have the result per worklet. We have the performance, which is unique, and if more is better or lower is better, the number of times the worklet was run, and the standard deviation between the results. In this tab here, we have the efficiency as we have computed it, so it means power per performance. Again, unique, always bad, what more is better, and the efficiency value of the particular worklet. And we also have the power demand during the whole execution of the worklet, all the time, or what we call try, that this worklet has been executed. In this particular case, all the worklet I present were executed 3 times. We configured the test to be fast, so we only have, or we have 3 results per worklet. For the purpose of this training, this is enough. Just another worklet, same performance, efficiency, power demand. And if we scroll down, at the end, we get the aggregated result, meta performance, the value that has been computed by the tool, and the power demand during the whole execution of the test, meaning all of the worklet. So this graph here is just a summary or just a connection of this graph and that one and so on. Okay, so now that we've remembered the web interface, let me show you how you can get the CSV file. Those files do not exist in any of the folders where you can get the result. You have to export them from here. So here we have many options, but the first one, result to PDF, to text, to XML, it's more or less the same you can see here in this whole screen, but just in PDF or text or XML format. Nothing new. I don't think they can be that useful to you. The interesting files are the 2 last ones, and in particular the last one. This one contains just a summary of the result, and the last one had all the power measurements obtained during the execution campaign. Let me first open this summary for a minute, because I want you to do a couple of numbers with you. Here we have the performance, the efficiency, the power demand for each of the worklet. This is, of course, average value, the average value of the 3 tries of this worklet, the same. And I want you to, we'll try to put 2 screens in parallel. Yeah. So that we can see the number. So now we will compute this value. As I told you, we can see these 2 arrows that point to the top, this one and this one. This means that these 2 worklets are higher is better, which means that their value goes directly to the computation of the geometric mean. So let me put them here in another column. So this one and this one. And for the other values, if you remember well, we have to just do the inverse of the performance and multiply it by 100. Okay, so let's do it. The 100 divided by performance. And we do the same here. Oh, sorry. There, and 3. Okay, here you are. So now, if we compute the geometric mean of the value that we have here, we get the result you can see here. So this is how this geometric mean is computed. As you see from the result, you can compute it by hand also. Okay, so now we've computed geometric mean. So geometric mean. Let's check what happened with the meta performance. So as I told you before, this is the geometric mean of the efficiency. Let's go to it again. Okay. In this case, we made the difference between high is better and low is better, but the value we present you here, so this one, that one, etc., are already the performances, which means that the transformation I presented in the slide has already been computed. What does that mean? That here, if we want to get the meta performance, we only have to compute the geometric mean of value that we get here without any transformation. We go there, close it, and we get the same value. So okay, now I've shown you how we compute meta performance and PROVAT and geometric mean of performance, but I haven't shown you yet how do we get the efficiency value for each of the worklets. So let's do it now. For that purpose, I will have to open the other result file. So let's do it. Open it. I maximize it. Wow. Okay. There's a bunch of numbers here, but what do they mean? Okay. Each column has a header. So in the header, you see what is in there. We have listed here all the worklets, all of them are there. And for each worklet, the first column is always the performance. So per each try, so 3 try, 3 values. And then we have one column of the power values per try. So try 1, power demand value. Try 2, power demand value, and here try 3, the same. Okay, let me reduce again. Try. So okay, so we have all performances, power value. If you remember from the last training, we told you that we configured the power meter to get values at 4 Hz. So 4 values per second. So just knowing the number of power value we have, in this case 23, we can get the execution time of the worklet. So in this case, 5.75 seconds. And in this particular case, we have one less value, so 5.5 seconds. But let's go first to compute the efficiency. So as we saw here, we present efficiency per worklet, in this case it was in number. How do we get it? Okay, the libjpeg worklet performance is more is better, which means that according to our equation, for higher is better, we only have to take performance and divide it by the average power demand. Okay, so let's check it. I compute I compute the average of the performance here. Now I will compute the average of all the power value we have. Okay, so let's get our efficiency. Performance divided, and here you are. We get the number we presented here. Okay, what happened now with this WORKLET in which fewer is better? In this case, we need to use the inverse of the performance. But let me first compute average of the performance. Here you are. And the average of the power value again. Average, and we have all of them here. Okay, what happens if I just compute the inverse of the performance, and then I divide it by the average power? Wow, we get okay, we get the right number, but you see it's very small. We humans tend to deal better with numbers that don't have so many decimals. So this is why we add just the scale factor here. If I go here and just multiply it by 10,000, we get the efficiency value we present here. And we could do the same exercise for all the rest of the WORKLETs. Of course, I will not go into it, but as you see, the computation will be the same. Here, the WORKLETs that are longer have more power values, but the philosophy behind it is the same. And apart from that, these are the results we provide. But with this number, you can do more things. Let's say you want to know the energy consumed by a particular WORKLET or a set of WORKLETs or all of them, whatever. As you know, energy is just power, sorry, per time. So we know the power value for each WORKLET, and we know the duration of each try, 250 milliseconds. So in this particular case, the energy consumed would be L1 multiplied by the time, 0.25 seconds. And then we can do it for all the duration of the WORKLET, and we can just get the total energy of the WORKLET if you want. So here you are. This is, of course, in watt second. And if we want to have it in watt hour, it's just we take previous value and divide it by the 3,600 seconds of an hour. So here you can see this Excel or this CSV file gives us more information that you can use for whatever purpose you have. You can do plenty of analysis with this, you can compute, you can If you use Microsoft Excel or LibreOffice or whatever, you can create your own plots, apart from the ones that we present in the web result. So there are plenty of computations you can do. And of course, for long tests in which WORKLETs are executed many times, you will have many more columns. So these files can, especially for long tests, can get really big. I think I forgot to mention you at the beginning that we have traditional columns at the end. They are simple. This one is just the aggregated performance, aggregated efficiency, sorry, the value I just computed using the other Excel spreadsheet. And the last column here is just a concatenation of all the power values obtained during all the executions of all the worklets. So it is quite a big column. This is useful if we want to display a graphic such as this one, for example, the whole power demand. Please bear in mind that these power values are only the power obtained during the execution of the worklet. So you know that between worklets there's a waiting time. Those values are of course stored by the control computer, but they are not presented here. Here are only the relevant ones. Okay, so now I've gone through the main result file. If you remember from the other training, there is one moment in which when everything is ready, you have to take out the USB stick from the controller computer and connect it to the unit under test so that the performance result and power result can be merged. How this is done? Well, if we go to the test results folder that you have in your USB stick, you will see that there is a CSV file called syspower.csv. This file is not intended to be modified or even read by the user. I will not show it to you because this is a big file. It's self-explicative, and you get all the information you need in the file that I already presented you. So in principle, you shouldn't use it. This file contains all the power measurements, sorry, all of them, even those values that when worklets are not running or when the execution of the test suite is finished, but you haven't stopped the controller computer. So everything is there with a timestamp. And this is why it's important to synchronize the clocks on both computers, because the merging is based on the timestamp. So here we have power result, power measurement with timestamp. On the other side, on the unit under test, we have measured performance also with timestamps. And the results are merged internally in the unit under test. Another thing I would like to tell you is here you can see an HTML file. Okay, please do not use it. This is an old version, it's obsolete and does not present you all the results. So this is the first way PHORONIX test suite presented the result, but it has evolved, although the file is still here. So please do not use it. When you open the result viewer, you are not opening this file. In fact, the test suite generates all this information in real time, and it constructs this web site and shows it to you. So again, just ignore this file and forget about it. And there are here in the test result, there are just other log files, composite.xml. This is the file that also is not intended to be read or modified or read by the user, but it has just all the information the PHORONIX text suite and need to merge the power result on one side and the performance on the other. In any case, yeah, the test suite provides it to you, but you shouldn't use it or view it in any case. Okay, so here at the top of the window, I told you at the beginning that there are more ways to export the result, but as you will see, they are just more or less repetitions of what we have in the main screen, in the result viewer. So there's no additional information. This is just summary if you wanted to do some sort of report, slightly more formal than a CSV file. But of course, this is not a file you will use in your analysis because you already have everything here. And the same applies to export to text file or export to XML or even text with XML, which doesn't add any additional information. And just to show you how a whole test suite looks like. So let me show you just for a moment a long test run. So this is test that we ran some time ago, and as you can see, we get all the list of all the performances indicating whether the higher is better or the lower. To compute it, geometric mean, taking into account what I just told you before. And here we can see that in this case, we configure the test suite with the default parameter, which means that it runs each worklet until the test suite considers that the results are stable enough. Why am I showing you that? Because I want to just do another export. Takes a while, just to show you this. So again, we have performance, power measurement, and as we have 8 performance values, which means 8 tries, we have 8 columns with power measurement. And the same for the rest of the worklet. The file is quite big, you can see. And at the end, as before, we have meta performance result 31859, which should be same value that you have here, and of course all the power measurement taken during the execution of the worklet. During Thomas' presentation, there was a moment in which he showed you that sometimes a worklet might not correctly run. It can give you, or it could give you an error. This worklet didn't produce result or something similar. Well, in this particular case, I'm showing you, let me find it, because in this case, this happened. And I know, what do I have to look for? Ah, here you are. What do we have here? We have the couple benchmark. We have one performance measurement, which is telling us that there should be only one column with power value. But in fact, couple here and there until there, we have 1, 2, 3, 4, 5, 7 different columns with power value. How is that possible? Well, in that particular case, when this worklet was executed, many of the time, at the end of the execution, we got an error of that worklet. For whatever reason, in this case, it worked one, but not the other times. So this is an indication if the numbers don't match, if you don't have as many performance numbers as columns here, this would indicate that something wrong happened with that worklet. So it could be, yeah, in this case, I don't know which one. I know that I can see that one of the execution produces a result, the other not, but I don't know which one. To that, you can always refer to the log file, or also what you can see in the result information window on your unit and the test, not on the computer fish, not on the, sorry, on the controller, but on the unit and the test. But in any case, this window is the same. Okay, so these are the main results. I still have an additional slide, because if you remember from last training, we explained you that the execution of one worklet several times produce, let's say, stable and repeatable result. Let's go through it again. So, for example, here, this is a good example. The worklet was executed 8 times, and you can see the power demand profile is the same during the whole execution of the worklet. And that happened with other, this one, also more or less the same. But what we didn't present you is how different can be results between different computers. And this is important, because at the end, what we want to do with the tool is just get a single efficiency value, and also performance, of course. But yeah, we want to get a single efficiency value that can differentiate one computer to another. At the end of the day, we would have one computer to be rated class B or class D or whatever. So this is a summary of results we have from some tests. As you can see here, we have some computers, different computers, and also same computer with different operating systems. In last training, there was a question, I'm sorry, I don't remember who, but someone asked us, wow, I get, if I run the same test suite or the same worklet different times on the same computer, I don't get exactly the same result. Yeah, we know it. Here you can see it. For example, in these cases, we run 3 tests. In these cases, we run 2 of them. And we never get exactly the same value. Yeah, we know it. We control, or we can control more or less what our test suite does, but we cannot control at all, or not sufficiently, what that the operating system do in the background. So there might always be some sort of process that for any particular reason requires a little bit more of CPU capacity or whatever during the execution of the worklet, which make the result different. But in any case, our results show that the deviation between the different tests is small enough to be able to put each computer in the right efficiency category. Of course, when we choose the final set of worklets to be used to categorize a computer, because if you remember from last training, we told you that for the moment we have 46 worklets. The current version of test suite can take up to 8 hours to run the full set of worklets, but we want to reduce this time in several manners. But one of the ways to reduce the time can be just to select or provide you the worklet that are faster, for example. And also, according to what we can see here, another criterion can be select worklet in which we see that the deviation of the result between different runs is smaller. Because I remember one question that I think it was the same person, he asked, okay, if I have, if I run the test suite several times, which is the result I have to use to provide an efficiency category for that computer? It's just the average, it's just the better, the worst. Okay, this is something that has to be decided. So for the moment, the tool just provides you the result. How the final categorization method will be, this is something still yet to be decided, but it doesn't impede you to just use the test suite and test your own computer with different configurations whatsoever. And okay, if we go a little deeper in this result, well, we can see that they are quite different. So we can see that in this particular case, the MacBook Pro, it was the most efficient computer we tested. Here you have the characteristics of them. And then we also have other values. You can also check that on a same computer. So for example, this one, the operating system is really important. It makes a difference. So you can see this particular case, and again here, this other computer results are better in Linux than Microsoft Windows. This, of course, is a particular set of worklets we use. So, of course, we couldn't try to install Windows or Linux in a MacBook. It is not that easy, but it can give you a hint that not only the computer, the hardware by itself, but also the operating system can affect the final result. So if you are, as a manufacturer, you sell computers with both operating systems, you will have to run the test suite in both of them, and it could even happen that the same hardware will get a different efficiency category and different performances if you sell them with one or another operating system. So, yeah, okay, so this concludes the presentation. here is the website where you can get all the information we've provided, the slide, our documentation, test suite manual. Can also get a link to the recording of both webinar and further information that we might get in the future will be put out there. So thank you for your attention, and just let's see if there are questions.
Thanks, Johan. That was fantastic, and I love the live Excel demonstration. That was really great to see. Okay, there's a couple of questions in the Q&A. Are you able to see that on your screen from Andrew and John?
Yes, I can see them, and I can also read them. So we have another follow-up from Anson Wu regarding whether it might be possible or make sense to compare the GPU accelerated rendering to CPU only. He says modern software will generally compute on the fastest available resource, for example, GPU acceleration in web browsers and Excel. Selecting the highest performance may be more representative of a whole PC, although you no longer compare CPU against CPU. You are absolutely right. I think I dismissed that idea maybe a bit too fast because web browsers are doing exactly what you proposed. They are using whatever they feel adequate to do their job. So they might use the GPU to render images or video or whatever, if it's available. Otherwise, it will use the CPU. If you wanted to have such a use case within our test suite with the Blender worklet, as an example, you would have to look up if Blender actually supports kind of a automatic detection of available hardware. If Blender can do that and use whatever it feels useful to run the test, similar to how a web browser does it, just detecting the hardware and deciding based on that. If Blender can do that, you can also do that within the worklet. But for that, you would have to modify the test profile to give Blender the instruction to do that automatic detection. Okay, then we have another question from John Sandragon Whites. I can't remember if the XML file that describes the results of the worklet had an indication of which type of value it outputs, LIB or HIB. Yes, it does. It is in the TEST-DEFINITION.XML file. Maybe, Jon, if you go back to slide 21.
Yeah.
Then we can take another look.
No,
I think you have a different
slide
set. Maybe it's 20.
It's 20, because I have.
Exactly. Here in the TEST-DEFINITION.XML file, you can see it in line 6. There is the proportion property, which in this case defines the worklet as LIB, lower is better. Yeah, you are right. That's an important property, and it has to be specified in each worklet. Otherwise, you cannot calculate the results. Okay, then we have a question from Stephen Eastman. He asks, when will this material show up on the website? I would say the presentation will show up within the next hour. For the recording, I think it will show up within a day. I think Mike has to upload it first and then pass on the link. So this might take a day. Regarding the software update, I think we still have a couple of days left until we release that. But this will then be also on the website within 3 days, let's say. Okay, and then we have a question from Dave Casano. Since the operating system is so critical to performance and efficiency and makes such a large difference in results, would running Linux on a Chrome OS system be representative? I mean, it depends. I would say if you do it the right way, then yes, because Chrome OS basically is Linux. So if you configure it in the same way as Chrome OS does, then of course, yes, it would be representative. If you configure it another way, so for example, that it doesn't do video acceleration properly with the graphics card, then of course it's not representative. Regarding Chrome OS, this is exactly the point. As we have outlined before, you can run our software on Chrome OS in the virtual machine, which is provided with Chrome OS. But of course, then you have the issue that the operating system changes, or you have an additional layer in between your operating system and the test software. So this is, of course, expected to change performance and efficiency. So in that case, for Chrome OS, it might be more useful to actually switch it to developer mode and try to run everything without virtualization. So this is something we are looking into it, but yeah, it's still a work in progress. Apart from that, we have also some good news to share for support for different operating systems. We have, in the last couple of days, looked into the new Mac OS X versions, and we think that we will be able to support Mac OS X 11 on Intel chips with the next version, and also support, at least preliminary, the new Apple Silicon chips with the M1 chips. I guess for the moment, most of the worklets are on the M1, still running with the Rosetta translation layer, but it's at least a step forward. You can run the software, you get some results, but of course, similar to Chrome OS, performance might be a bit lower for those worklets running with the translation layer. Nevertheless, we think that this, at least for the moment, is a fair assessment, because users will have the same issue, let's say. They will use their software which they are used to, and if the software is not yet ported natively to the device, it will have the same problem, let's say.
Hey Thomas, you said that the new software would be posted in the next 3 days. Will what you're just describing there, this update, be included in that new version?
I would say that the support for Mac OS X 11 on Intel chips will be included for sure. For the support for the M1, there are still a few things to iron out, and we want to take a look at how much we can get to work without the translation layer. So yeah, we will see if that is included, but at least for Intel MacBooks, the support will be included.
Great. And I was looking at Dave Casano's question, and I wasn't sure if he was suggesting to run Linux on a Chrome machine, or if he was talking about the layering. Dave, I'm just going to unmute you for a second and give you an opportunity to just ask a follow-on if Thomas didn't answer exactly what you were asking. Go ahead, Dave. Dave? Maybe you've stepped away from your computer. I saw you mute and unmute yourself, but we can't hear you. Sorry. Maybe we'll come back to you. Shahid has asked, when will the 3-hour test be released? Can you give us an update on that, Thomas?
Yeah, it's a bit difficult. We have to find the right time to actually change something in the worklets. So I'm not sure yet if that will be included in the next update, since we mainly try to address the feature requests we have received in the past, which can be addressed relatively quickly. But of course, changing the worklet or the configuration of the worklets is an important step, so we don't want to rush that out. So yeah, I cannot promise that this is included in the update.
Great. Okay, great. So it's work in progress, Shahid. And Dave's just written us a note in the Q&A that his question was answered. So thank you, Dave, and sorry about the sound issue. Okay, we are 3 minutes from the end. Is there any other questions or anything else you guys wanted to say from the GTD side?
No, not from my side. I think if there are no more questions, then this would be everything from us.
Thank you, Shahid. Yeah, great. Well, then we'll give you all 2 minutes back. Thanks everyone for attending, and we'll be posting this up just as soon as we can, and look forward to keeping in touch as we take things forward. Have a good afternoon.